All right, so we're live. Well, hello everyone. Thank you for joining us for this month's EPSP Connects. The purpose of this series is to bring the community together. Not everyone's always able to attend conferences, etc. So we're hoping that you can interact with colleagues in the community through a different, approach. I'd like to thank all the EPSP Connects volunteers who help run this series, get in touch with potential speakers, organize panels, advertise on social media, post everything online, etc. It's through us, I'm including myself in that list of folks that help run this thing. So thanks to all the team. And joining me today, co-hosting is Tyler Doan. So feel free to introduce yourself, Tyler.
Thanks, Roberto. I'm Tyler Doan, co-hosting with Roberto today. I just want to mention that as the talk progresses, if you have questions that come up, please don't hesitate to type them into the chat and we will read them out after the talk. Or at the end of the talk, if you want to raise your hand and unmute yourself, you can ask directly. We also are streaming this over on YouTube. If you happen to be watching over there, we will monitor over there for questions. And also, if you happen to be watching this recording at a later date, feel free to reach out to our speaker today with questions if they come up. I'll turn it back to you, Roberto.
All right, thanks, Tyler. So today's speaker, Dr. Catherine Russell, thank you very much for joining the series. Catherine's a geoscientist specializing in the impacts of human activity on Earth surface processes during the Anthropocene. And there's a focus on river systems. Dr. Russell got her PhD in fluvial sedimentology and became a fellow of the Higher Education Academy with distinction. A couple of years ago, Dr. Russell was awarded a Fulbright Lloyds of London visiting scholarship to the University of New Orleans, where she researched pollutant accumulation in fluvial pathways. She has established many collaborations across the US and the UK, and holds honorary positions at Louisiana State University and Loughborough University. Um, she founded and leads the Anthropocene Sediment Network. So if that's something that's of interest to you, feel free to reach out. And with that, Catherine, I'll let you take it away. Thank you.
Thank you, Roberto, and thank you very much to the committee for inviting me to do this. It's really great to be here. So today I'm going to be talking to you about sedimentological insights into how we can improve contemporary environmental assessment. And what I mean by this is, so I'm a sedimentologist by training, but we sort of run out of words when it comes to things that we have added to the environment. So I'm just going to sort of share some of these thoughts with you. So we've impacted all areas of Earth, if not primarily and physically, then through secondary impacting of changing the climate systems and such like that, which has been widely recognized by groups such as the IPCC. We have changed and continue to change the geology of Earth, and there's kind of this belief almost that the geology is unchangeable because it's so solid, because it's made of rocks, but through withholding water in dams and reservoirs, mostly in the Northern Hemisphere, we've changed how Earth moves on its axis. We've strip mined the tops of mountains, which will take about 200 million years to replenish, but realistically, those mountains are never coming back. Major cities are heavy and change the shape of the Earth's crust, and we've changed the intensity of earthquakes in places such as the San Andreas Fault by pumping fluids down to help it to run more smoothly. All of this is changing the geology of Earth. However, we've got this surface layer of material and sediments and things that are readily moved by processes and systems, and these are by far the most affected in the geological system, which means that uniformitarianism, which is a geological concept which referring to the fact that the present is the key to the past, is getting harder and harder to justify because the world now is almost unrecognizable to 100 years ago, let alone 1,000, let alone 1,000,000, etc., all the way back to 4.56 billion. So the planet is overwhelmed with trash and other anthropogenically made or modified materials, much of which is technically sediment. So the device that you are watching this on, anything that you have in your hand, maybe your phone or computer mouse, will end up sequestered somewhere at the bottom of the ocean or somewhere on land in the future. This is a very temporary phase, and if we think about the difference between, say, chucking a rock in a river or chucking a plastic bottle in a river, the river is not going to, say, transport one and not the other. It's all materials that will be transported on Earth. So we need to somewhat find a way to comfortably grey out that boundary between what is sediment and what is us, because it's all sediment components of the sedimentary system. Traditional sedimentology doesn't fully account for these new human-made materials, and environmental assessments are lacking in methods to meaningfully integrate these materials into their analyses. So without a sedimentological approach to consider these materials, the human-made materials, we cannot fully consider their risks and impact on our present environment or their long-term legacy. And these are clearly important things to do. So this presentation is going to be in three main parts. The first part is going to be basically saying, is there a problem? Is there a reason why we need to care about anthropogenic materials in the environment? Spoilers, yes, but I'll prove it to you. Second one is looking at methods to consider plastic as a sediment. And the third part is looking at anthropogenic sedimentary facies. So if any of these words are new, it's fine. We'll cover it all step by step. So we're going to do this bit first, look at the extent to which plastics can impact sedimentary processes. So last year, I published with Roberto on plastic pollution in riverbeds and how they're fundamentally changing natural sand transport processes. And this is kind of, this piece of work came about, showing because we saw so much plastic pollution within river systems, but very little work was being done on what was happening on the riverbed in the area where we would consider to be sort of those kind of interfaces between the natural sediments and human-made sediments. But we have very little information about what's going on down there. So these preliminary studies that we did indicated that significant further study is required. It got quite widely talked about and front cover article in the Geoscientist magazine. And this is just a small clip to show you a little bit of what was going on. So if we keep an eye, I don't know if you can see my cursor, but on the stuff side of this dune, you see there's a piece that's just blown out, and that's left a shape, an erosive part, an eroded part to the back of this dune. And you'll see that as it continues to migrate, it's changing its shape. And what this means as we continue to watch it is that this dune is actually becoming flatter over time. And that's important because it means that it's changing the roughness of the riverbed, and it's also changing the way in which it will be able to migrate and trap sediment. And any fish, for example, or anything living on the bottom of the riverbed relies on these topographies in order to survive and spawn. We've got another one about to go here. These are just cigarette filters, by the way. And yeah, and then we'll see that this actually continues to flatten out. So this is a collapse of a bed form. None of this is sped up, by the way. This is real time. This is the collapse of a bed form due to the fact that we've got these materials in it. And it's three factors of these materials that causes this. One of them is that they are of lower density, but it's also because they are quite smooth. And therefore, as soon as you start to erode part of it, then you erode all of it. So they've got very low roughness. And it's also to do with the fact that they can block and erode and cause scouring, further scouring and such. And so they have a low erosion threshold because they'll readily re-enter the water column. And so you can see that the jump from that to back to this, it has changed. So we can end up with basically a fundamental alteration of these bed forms because of plastic inclusion. So we find that this plastic material on riverbeds is not passive. It definitely needs to be considered, and it's clearly an important now sedimentary component. The plastic inclusion is changing the ratio of suspended load to bed load material, because every time there's an erosive process, some of that bed load gets resuspended and becomes suspended. Inclusion of plastic is encouraging rivers to develop more conduit-like properties, which means that the material will go into the river and it will just continue going down. So conduit-like properties is in contrast to storage properties. Of course, this varies depending on the flow conditions. If it's a big flood event, of course, it's going to be more conduit-like rather than storage. But this is kind of showing us its capacity to allow materials to pass through even at any flow rate, because that was again consistent flow. So we founded a new subdiscipline of sedimentology, which is plastic and sediment interactions. The next study I'm going to show you, just to kind of keep going on this a little bit, is to show you how we need to quantify these effects and enhance our base level understanding of these interactions, because of course this was just preliminary work. So through these increments, going from 1 up to 11, we're adding different amounts of beads into it. So by percent, we mean non-tessellated bead cover. So if the bed form was completely flat, what percentage of the surface of the bed would be covered by beads that were not overlapping just along that surface. So these are all Mardi Gras beads that were individually hand cut, 49,000 of them. They're all 7 millimeters across, and the reason for us choosing to use this material is because they were everywhere in New Orleans, and a lot of the drain systems are clogged with Mardi Gras beads, so it seemed like an important thing for us to start looking into. Each increment was at least 16 hours apart, so it had definitely had time to calibrate, and the flow speed was constant for the whole experiment. This is just showing how it went upwards, but just notice here at 20% bead cover, the total beads to total sand ratio is still very, very small. So we're talking about tiny proportions of this that can have impacts. This is just a slowed down version showing some of the data that we collected. So I did a sheet laser and looked at the sediment flux, and you'll see some little pink dots going across on this upper blue part here. And that's one of the jobs, is to start counting some of them to see how the flux changes depending on the amount of plastic that's actually in the riverbed. And of course, this is still ongoing work, so I don't have all of the answers for you yet, but I will do soon. This is another video just to show kind of how some of this material moves around. So this is from 2.5%. So this is the graph that we saw earlier. So this is 2.5% non-tessellated bead cover, assuming the bed was flat. And we can see that we've got some of it in the bed here, but we're just going to watch this group. And you can see that rather than going downstream, so flow is going from this side to this side, from right to left. And you notice that they actually move upstream. These beads have gone to have got caught up in a recirculation zone here at the along the dune, and they've actually moved upstream. And not only that, but this area where they were eroded from, because they enhance the erosion, because they are quite large scale, they've actually started to create this scour pit. You notice on this side of the next to the downstream dune that they eroded from. So not only are these beads moving upstream, we're actually seeing in real time, this isn't sped up at all, that they are quite significantly enhancing the scour because of their erosion. So it's less about the inclusion of the plastic materials within these bed forms. It's more about how they are being removed and enhancing some of that change. So we have to understand the structure of how these plastic materials are in these bed forms, what shape they are, what their properties are, and how therefore they're going to be impacting these sedimentary systems, because now we can see that that is quite a significant scour of just happened in literally, what, a minute. So when we're looking at these large bed forms, just to show you what the tank looked like a bit more, we saw a marked change in bed form morphology at about 12.5%, and 20% bead cover was the upper limit, because the increasing slope change within the tank is actually seeing the bottom of the flume tank. So we had to make we had to call it the maximum at 20% cover there. We see an increase of morphology, an increase of bed form diversity as the concentration of beads is increasing. And we found that the same mechanisms that were actually causing the smaller bed forms to occur were happening on superimposed bed forms in these larger ones as well. And I've skipped over the smaller ones for this talk because we've got other things to talk about. So just to show you some of these preliminary results again, all of these are the same slope, by the way. It's just screenshots. So at 0% beads, when this was just your natural bed form, we've got a nice regular set of bed forms in there. But then at 10%, we're starting to see some disturbances, and you can see that we're getting some deeper scouring. At 12.5%, we can see exactly what we've been talking about, with more of these scours in the stoss side of these dunes. And then by 20%, the beds are being constantly disrupted, constantly trying to return to that natural equilibrium, and then being disrupted again. And yeah, bear in mind, this is still a tiny ratio of plastic to sand. So it's yeah, I have lots to write up from this. Again, watch the space. It will be appearing soon. The other thing about this is thinking about how this relates into real world sampling. So for one of those dunes, on the surface of it, at the end of the experiment, I went down and picked off the beads from the top of the dune and found 65 from the surface and 3,310 from in the actual bed form, which means that about 2% of the beads were actually visible. So if we scale that up to large scale rivers that we would expect to see rather than something in a narrow tank, if we're using sampling methods, for example, such as a Van Veen grabber, where it goes down, grabs the sediment, comes back up, we're probably not seeing the full extent of what is down there. And so we can use these kinds of sedimentological integration to really better understand where the pollutants are, why that's important, and how it might be affecting the biota. So even under constant flow speeds, these beads are constantly disrupting the bed form and associated flows. These very small bead volumes are having high impact, and only around 2% of the beads are visible on the river dune surface. So we need to reach a point where understanding where plastic and other pollutants can be fully considered and integrated into models as a sedimentary component. But this leads us to a massive problem that as soon as you get to anything complicated that can't be considered by a grain size card with the scales, with the, is it a granule or a grain or a small grain, or is it, as soon as we get complicated beyond those basic concepts, we don't have any language that is appropriate. So studies are increasingly, so yeah, this brings on to the second point of the talk. We're going to start considering plastic as a sediment because we need to have that language to do this communication. So studies are increasingly seeking to understand plastic routing such that the passage of plastic into the natural world can be mitigated, and the importance of a unified classification scheme cannot be overstated. Classification, therefore quantification of anthropogenic material is challenging because it can be any combination of properties imaginable. It's more complex than just adding plastics into sedimentological models because of the difference in properties. It's not just about density. It really is so much more complicated than that. And they change the way the sedimentological processes work. There is a lot to research. Existing schemes work really great for the projects that they were designed for. But to unify them in this context, we need to be finding ways to consider plastic as a sediment. So why sedimentology works, and why I'm kind of using this as a grounding method, is because we have these, I think, these three core philosophy objectives. The first one is we do objective analysis before any interpretation. So a name such as bottle is an interpretation of its prior use. Any material, and also because things are being named, say as bottle, as they fragment in the environment, as soon as they stop looking like a bottle, they suddenly become miscellaneous. They become a fragment. They become something different. And that means that as these materials are growing more and more, the miscellaneous bucket category is going to keep growing as well. So we have to describe things before we can before we should name them so that we can see the genetic decomposition and genetic changes that are happening through the environment. Because say the bottle is red and we haven't described that the bottle is red, but we suddenly start seeing a load of red microplastics, through that classification, it will look like those red microplastics have come from nowhere, and they haven't. They've actually come from the bottle. So we have to genetically understand how things are happening. These are 3 bottles, for example, and they shouldn't be under the same classification system, and because they are fundamentally different, made of different things, of different purposes, going to have been sourced from different places. etc., etc. So we need to have a more nuanced understanding of what we're actually looking at. We also have a deeply rooted allowance of temporality. So sedimentology can be used to understand deep time, deep future, and these temporal transformations of particles and environments. And there's also, quite importantly, a systematic and consistent flexible framework. So even though we have these central standards for observation for the way that we'll look at a grain, there is a huge ability to make additions into the scheme so that we're still working from the same like center trunk channel of the tree, but we're actually adding in things like, well, as well as this, we need to look at this feature of this object. And so it's very logical and objective, and it enables this consistency because we keep rooting back to the same key factors. So so there are 4 key factors that we're going to look at. The first one of them is size. So size itself is completely objective, widely accepted how we measure things. Nomenclature is very variable, which unfortunately makes it interpretive. So if we're talking about microplastic and mesoplastic and macroplastic, a piece of plastic, for example, that's 5 millimeters, depending on which study and which classification system you use, it could be micro, meso, or macro, depending who you're looking at. And that's a problem because it means that these words have have lost some meaning because the scales are different. So to standardize it, we've made sure these categories can relate to sedimentary deposition. So this section here of meso and macroplastic is relating to frequently used household plastic objects, which are between 5 millimeters and 1 meter in size. You'll notice that your household refuse bin is a size that can contain those items. And if you think backwards through everything you've probably handled today, it goes into these categories of scale as well. You probably don't use things that are over 1 meter in size on a daily basis that will go into your garbage bin, which means that landfill sites will primarily have this scaling of plastic material as their input. And we've also added gigaplastic to refer to objects over 10 meters, because this speaks to commercial trash sites as well. So places where we might have a lot of the same thing that's all being decommissioned. Shape is kind of a really interesting one because we have this one from sedimentology with high sphericity and low sphericity and then varying levels of angularity. This is perfect for microplastics, but then we have issues with scaling this up because not everything is of natural kind of sphericity. We can use this elongation and flatness thing so that we can look at whether or not an item is a disc, a sphere, a blade, or a rod. That's really useful. However, what is perhaps more useful than this for the plastic studies is this roundness and texture, which is new to the paper, where we're actually looking at, we can look at a corner of it as well. So we're not assuming sphericity here. We're also looking at, say, you could have something that is a blade, but actually all the corners are really rounded off. And so we can talk about it as a rounded blade in a more easier sense to translate it from this. Then we've got the density of scratches on the surface, the intensity of those scratches and textures on the surface. So this can all help us to start to identify perhaps some of its passage and tracking through the environment. Then shape is incredibly, this was the hardest bit to come up with because anything can be any shape. There are 3 core types of hole, and we've done the shape by holes because it is just the simplest way to do it, and it's got some mathematical basis to it as well. So we can have a through hole, which means that materials can pass all the way through. A blind hole, which can cause some secondary turbulence, but it's also somewhere that creatures could live in a sheltered environment. And then we have a closed hole, which is possibly the most impactful because that can alter the buoyancy of the object as well. So if we can identify if we've got through holes, blind holes, and closed holes, then we can start to identify some notations and the way in which these are changed within, can occur within the environment. This is called topological homeomorphism because we have an object which has got a topography to it, and it is homeomorphic, so it changes shape. It can change shape without breaking the surface. So a blind hole is a hole that can be removed from an object without needing to break the surface. So if you imagine this made of blue tack, it's a lot easier. It explains it quite well, I think, in the paper that we have coming out, and takes it all through step by step. And feel free to get in touch with me for any questions as well. But one of the jokes is that topologists in mathematics don't know the difference between a mug and a donut, and this is why. Because the through hole will always be there, and that's how to identify a through hole. It's always there. You can't get rid of it without breaking the surface, whereas a blind hole can be got rid of, and a closed hole is something, of course, that's closed from the environment. This is really important because, for example, if we look at these bottles here, this is a blind hole in this one because we've got the lid off, and therefore it is more likely to be neutrally buoyant in the environment because it will fill with water or whatever is around it and behave very differently to this one with a lid on and a closed hole, which is more likely to float. So these two bottles may wash up on completely different beaches, perhaps even on the other side of the world, because of their topology and the holes that they have. This is to emphasize this as well through the next step, which is the absolute density. So once we have the shape and we know the scale of it, we can look at the absolute density. Every single one of these bottles along the top has got the same polymers, but they are not going to behave the same in the environment based on those polymers because they have got their lids on and they're full of different volumes of stuff. They will have different mobilities. These ones will be negatively buoyant. The one that's full of water will be neutrally buoyant, and these two will be positively buoyant. And therefore, of course, they're going to end up washed up in different places. And so absolute density, which considers everything inside the bottle, as well as the polymer, is really, really important when we start to consider these as sediment. Of course, polymer type is important, but yeah, we have to include other stuff as well. And if the lid is off, then there's a possibility for this to change. So as soon as you're doing any kind of environmental analysis, you wash it, you empty it, you shake the materials off, you dry it out, the depositional properties of this object are lost. And so we've got to be really careful with how we do this and try and do it as in situ as possible. Last but not least, we've got material properties. And this is where we look just to see, is it brittle or plastic? So can it bend, or is it going to be really brittle? This will tell us about the types of material that it can make. It tells us about whether or not it could wrap around something like a tree, or whether it's going to start chipping materials away and therefore create microplastics far more readily. It might even tell us how long it's been weathering for. If it's opaque, then that's different to it being transparent. If it's transparent, different creatures might be able to live in it. There might even be a warmer environment inside the bottle. Is it flexible or elastic? Is it static or hydrophobic? We've got a lot of questions that need answering, and all of these are sedimental properties of the sediment, and they are things that are considered within some of these fields already. So this is just a summary of this part, and then we've got one more section of this talk to do. So in assessing the size, the shape, the density, material properties, we can better understand plastic as sediments, and then we can start answering really advanced questions from where these properties are appearing in the environment. None of these properties should be considered in isolation. That's super important because, of course, this is a combination of properties. We normally do a full rock description, so we should do full material descriptions on these as well. And then, of course, intergrain relationships is the next part we're going to look at. This is just the top section of one of the sheets that comes in supplementary material in the manuscript that will be out soon. We talk about the axes, and then this is just everything that we've just talked about going through and making sure that we're recording everything. So if we're looking at these intergrain relationships as to where these things get deposited, this is where it becomes what we're calling sedimentary facies. So it's effectively the rock type. So typical sedimentary facies are things like a mudstone or a sandstone, and we need new words and things to describe what we've done because we're creating new types of stone. So in 2020, the collective mass of human-made materials surpassed that of Earth's total dry biomass, which suggests that a significant portion of sedimentological record being formed today could comprise of anthropogenic materials. So what this means is that a future geologist looking back at 2020 in the rock record will find that 50% of the fossils will have been human-made because we surpassed that at that point. So dry biomass, that's fossil biomass, 50% of the stuff will have been human-made. There's a 50% chance of finding something that was actually once alive or something that we produced. That's huge. And that means we definitely need words for it all. Yet the investigation of these distributions remains incomplete, and it hasn't really been a priority for geologists because this largely falls under engineering. But we are really starting to see that this is going to become part of our planet. For example, this is a sedimentary layer from Mardi Gras. This is an image courtesy of Brett, who works for a grounds crew over there, trying to replace this wasteful culture with reusable and eco-friendly objects and things. This is genuinely incredibly typical of what Mardi Gras looks like after a big parade, unfortunately. So these bins are overflowing and we've just got these layers. This is obviously quite an extreme example, but I'm sure we've all been to places where there's been a lot of trash and we've thought, wow, and we look away. So all disciplines that are tackling human-made materials have got a very necessary specialized focus. And of course, this is just going to be one of many focuses on this. Archaeologists are considering anthropogenic materials as artifacts, but the sediment surrounding the artifacts is not always considered, which means that sedimentologists are missing some of that context. Soil scientists are considering anthropogenic items as classed under the FAO guidelines, which do not specifically address the classification of anthropogenic materials or contaminants in soils and sediments. There is a plastic inclusive framework that Weber produced in 2022, but only plastic is delineated by the scheme, and we have a lot more that needs to be included as well because we've made a lot of stuff. Engineering geologists will use terms such as anthropogenic fill, made ground, artificial ground, and these are all good terminologies to use, but they are too generalistic to really understand the origins and future of the deposit in a similar way so that sedimentologists can use the skills that we already have with using those words. Environmental sampling is undertaken on a lot of materials and chemicals, focusing on quantifying mass, form, and composition. But we cannot form a unified sedimentological perspective from what exists, so we need an integrated classification scheme that can capture the full spectrum of anthropogenic impacts on sedimentary environments and, importantly, also be flexible. The potential of sedimentology to further enhance this understanding is substantial and relies on robust classification framework. So this classification scheme mirrors the adaptability and framework of traditional sedimentology. The setup of it is similar. You can use all the same skills you have as a sedimentologist to do all of this, and it's appropriately designed to provide a robust foundation for descriptors and nomenclature, so the most appropriate FASCI scheme can be developed to meet specific objectives of the study. And the framework specifically focuses on the description of field-scale sedimentological things, which can be inexpensively done in any environment. You don't need any special kit. So this is just going to go through point by point, same as the last scheme, talking about the different features and things that we see. The first one is the composition description. Point one, we've just covered with the previous part of the scheme. How do we describe the anthropogenic material? That's the first thing. Second thing is to look at the sediment and soil surrounding the anthropogenic material. So do a description of the soil of it, the sand, whatever is going around it. And then if you've got any closed or slightly buried sections within the plastic, any material that's within the anthropogenic material needs to be described as well. Then we can look at things like bed or lamination scales. So this is scale independent, and then grain scale. Bed lamination scale is anything that is strata forming, strata containing, strata surface modifying or subsurface modifying, consolidated or unconsolidated, lithified or unlithified, compacted or non-compacted, and then giving the overall bulk density of that material as well. So you can have a strata-forming low bulk density material on the top, which might be something like a landfill site. But then you can have consolidated and lithified strata-forming subsurface materials too. So there's a lot of ways to describe this, but then of course we've got into the grain scale materials as well. And so you can have, what's the porosity, permeability, sediment matrix. A lot of this is very common across sedimentology, but then we get to things like, structures controlled by sediments or structures controlled by anthropogenic materials. So for example, this is supposed to sort of represent fabric or clothes or something like bicycle tires that can readily change shape and fill up with sediments around it. And so the structure of that material is actually dictated by the anthropogenic material structure as well. So is it well sorted? Is there any orientation? We can ask a lot of these similar questions of this material. Then we have sedimentary structures. So we've got them either being bound or unbound to begin with. And if they are bound, they may be contained. If they're contained, then they are enclosed in their surrounding layer, so they cannot interact with the environment. They haven't been able to for the duration of their journey. And that can be something like a trash bag. If it's uncontained and bound, it may be combined, so gathered together, such as these bundles, and it's structurally bound as a unit. Both of these two will have been bound before transport and deposition. Then you can have things like a tangled fishing net, which is bound before and during deposition, or something like a shopping cart in a river, which is bound during deposition because it's baffling the materials going through it. Then everything underneath here is stuff that we commonly see within sedimentology, but each of them gives us a slightly different kind of interaction or stage within which the plastic may have been introduced into the system, and allows us to really understand, some of the materials and this interaction that we're seeing. Of course, we have a lot more to learn about that because if you've seen, there have been 2 experiments so far looking into what some of these interactions are. But just as looking at whether or not these are massive or layered or anything like that, this is just a way that we can start to have these descriptions. This is not supposed to be the end result. This is supposed to begin a conversation. And then last but not least, we have nomenclature. So we have to be able to talk about things in a similar kind of way so that we can ensure consistency and connectivity and have these interconnected research collaborations. As we saw right at the beginning with different terms for sizes, it can create a lot of disparity between working groups, and we need to be able to make sure that that doesn't exist for as much as possible. In geology, we typically base nomenclature on the mineral composition of the sediment, and that's what's mirrored here. And it's a continuation of the emerging nomenclature preferences of the community, such as plastiglomerate, which was coined in 2020 by Patricia Corcoran and Jaswak, plasticlast and plaster sandstone, which were both coined by Rango Buitrago in 2023. And of course, there were combinations as well. So you can add anything logically because that's the process of being able to develop this in a sensible and logical way. So we have prefixes on one side and suffixes on the other side. And if we are looking at the mineral composition, we've got silice, which is silica, organic, or carbonate at the beginning. So where we have greater than or 20% sediment or less than 80% anthropogenic material. I'm having to do this with my fingers because I can never remember which. I'm terrible. But just looking at these, so we've got silicoplastics or silicoglastic, depending on what the material is and what the mixture is. So we've got mostly sand if it's got 80% anthropogenic material, less than 80% anthropogenic material, sorry. Then we've got silicoplastic. So yeah, and then when you have it the reverse the other way around, then we've got things like plastiglomerate or plaster sandstone, because we've got majority of that is the mineralogy. So everything that's on the left-hand side, the prefix, is the dominant mineralogy of what's going in. And then anthro is kind of a bucket terminology that we have to use so that we are acknowledging the fact that it's a human-made material. To apply this then, here are some examples of things in the real world. This is oyster shells that have been combined and drawn together to build reefs off New Orleans. So this would be a combined anthrogglomerate. This is rack that has come up on a beach in Cornwall and it's full of plastic, most of which is neutral buoyancy. And that's a massive organoplastic. We have a shopping cart from Asda by the looks of that. That's a very UK reference, if anyone knows what Asda is in the UK. Sorry, I forgot. And then we've got a lot of material behind it. So that's a baffled silicometallic clast. Then we have a load of Mardi Gras beads stamped into the soil. That would be a massive organoplastic. This is part of a landfill site. We've got some concrete down here and rebar and also some bricks and old construction works. That would be a layered anthrogglomerate. And this is from some of the flume tank experiments where we've got a dune passing through and then some beads in there as well, which would be a unidirectional silicoplastic material. And then we can use all of these terminologies to continue to describe what we see in these sites so that we can actually start to have some really deep and meaningful descriptors and discussions that can go interdisciplinary. So to summarize, Plastic in the environment can fundamentally alter natural sedimentary processes. To learn about this, we need a unified sedimentologically centered approach, which really needs a solid language. A pair of thoroughly researched and adaptable classification schemes are proposed that are based within recognized approaches. They will provide a structured method for categorizing and analyzing anthropogenic materials within sedimentary deposits. And by allowing for these novelties in sedimentology, a more nuanced understanding of the impact of anthropogenic materials on our environment, such that we will learn more about the significance of anthropogenic influence within the stratigraphic record can be met. So these are the two cheat sheets that will come with the manuscripts. This is from two different papers. This one will be out first, followed by this one. This is a huge new subdiscipline to sedimentology and geoscience, including these plastic sediment interactions, which need interdisciplinary knowledge and collaboration, and is the underpinning fabric of what will become Anthropocene sedimentology. If you are interested in any of this or using these, please do just drop me an email. We have the Anthropocene Sediment Network, which is Roberto plugged at the beginning, but please do get in touch if you're interested in being part of this work. Thank you very much.
Thank you, Catherine, for a really excellent talk. That was really just impressive and motivating, and also a little bit disturbing. We do have a couple of questions in the chat. We have one from Vanessa Garcia Gamero. Considering the first section, I was wondering if the different tests with plastic beads have been tested on different riverbed materials with different composition. And she thanks you for the talk and the organization.
I mean, that's a fantastic question. We only did it with sand, and we only did it with Mardi Gras beads because to run an experiment with 11 increments with 16 hours between each increment, it takes a long time to go through each of the iterations. So anyone who's like willing to or wanting to do further work, there is more to do than any one researcher can do in their life. So yeah, anyone that's interested in it, yeah, if you want to do the work, do it. It's fine, it's great. Sounds great.
I guess we have a question from Julia. Yeah, go ahead.
Hi, Catherine. Great
Hi.
talk. I'm so happy I was able to jump in and see this. I missed the beginning about a network or something. I totally want to join. Please, I'll email whatever I need to do. You know what I'm going to ask about. I'm sure you do. I love seeing the experiments. I love seeing the way that you've put processes that you've seen with the plastic and like the bursting and things like that. I think that's so valuable. And I know that those are the only experiments you've done, but I just want to pick your brain and hear what you think. Have you considered how different scales of plastic will interact and will influence these bed dynamics? So for example, do the micro scale plastics have that same buoyancy bursting process, or do the bigger plastics that you mentioned, like, I don't know, maybe the meso higher order ones, would they act more as obstacles as opposed to something that is building within the bed and migrating with those bed forms? And with that in mind, how, with all these processes that you've described and the ones that I've asked what you're thinking about, what do you think that means for sediment transport within these environments? How is that going to influence the larger scale sediment transport through these conduits?
Okay. Thank you for the questions. They're great questions. I think I'll start by talking about the different scalings of plastics in the experiments. It's actually a really good question and really interesting. I think the main thing that was perhaps a limitation for me being able to see some of those increments is that we use the same flow speed throughout. I think if you were to start adjusting into a seasonal flow speed, you could get some really interesting stuff from microplastics. So for example, if you allowed deposition to occur in a slow flow speed, and you would be able to settle microplastics that actually had a significant density difference, because the microplastics that we used in the first experiments didn't have that big a different, well, they did have a big density gap, but there could have been a bigger density gap between them and the other ones. So I imagine you'd have to use more to get that same tessellation, non-tessellated kind of cover for the percentage differences. But yeah, I'd imagine that you could get an impact. I don't know how that would be necessarily different. But yeah, there's definitely something there. With the larger ones, it's quite interesting that once they become part of the bottom of the bed, they'll actually roll by traction for quite a while. But for some of the larger ones, once they start to get buried, they actually make their own little scours and kind of bury themselves. You know, yeah, they kind of they just sort of sink themselves, and sometimes they'll even roll upstream. They don't care what the river's doing. So some of these larger materials will actually have very, very interesting things going on. If they're larger and they're floating and they start accumulating on banks and things like that in the real world, so you started asking like, how does this affect things in the real world? These are all things that are, as far as I'm aware at the moment, largely speculative, and we get in the way a lot in the real world. If you go and find an urban river, we are constantly intervening, and a lot of this is through litter picks and stuff, which is actually fantastic, and we need to be getting rid of the trash. But you know, I want to see what the trash does, so just leave it for a few more days. I'm joking, but like it's kind of just, you know, making sure that we can find a way to safely examine some of this that's outside of the real world, because yeah, it's harmful for as long as it's in the environment. So it's actually quite difficult to try and find sites for. But yeah, I don't know, lots and lots of questions. There is actually some really cool stuff being done with shopping trolleys, where they kind of become reintegrated as part of shopping carts, sorry, in America, where they've been reintroduced into the environment because they become so filled with nature. That's been going on. I think it's Anne Jefferson who works on that actually, so that she'll have more answers for you on that.
Thank you.
While we wait for more questions to come in, I have a question. Can you mentioned briefly the material properties and like the flexibility of the material, and there's so many more variables to consider than we typically do. Can you just elaborate a little bit more on how you think about like a plastic bag or a tarp or things that are, how would you first describe the size of a tarp that can be folded up into something much smaller, or it could be 10 meters? How do you tackle those challenges, or how do you envision them being tackled?
So in the plastic as a sediment paper, one of the things that we do say is that leaving things in situ is really important. So for example, with an example of the bottle, right? If you find that the bottle has got its lid sort of still attached to the collar part of it, you found it like that. So don't put the lid back on before you start measuring the properties, leave it as it is and start assessing it like that. If the tarp, for example, has sort of tangled itself up with ropes and stuff, you assess it like you find it, because you never know what the transport condition of any of these materials are. You only know their depositional status. So if you're looking at the tarp that is as is on the beach, you can only assess it as is. If it's over 10 meters, then fine. But if you, for example, find a rope that's all coiled up and it's clearly been coiled up for its whole life, if you unravel that, it's a statistic that doesn't mean anything about its transport, because you've simply measured your actual morphology of it rather than how it was found. So there's some pragmatic decisions that have to be made about it. There's also a really interesting case to be made that if we're introducing everything anthropogenic as sediment, that there's actually a huge range of biological materials that are also sediment too. So things like an old dinosaur carcass, for example, just to go for the most gross example straight away, but a tree trunk or anything of these different scales, there's actually a huge amount of stuff that's out there in the environment that when you start thinking, that's behaving as part of a sedimentary system, it becomes a lot easier to start imagining the way that we might start, what the impacts of that on the preservation of the system or the process might be, and so therefore how we can start adapting what we know, if that helps.
Yeah, definitely. Thank you.
Roberta's just shared the preprint link for the paper in the chat. Thank you.
Okay.
Oh, yeah.
I sent it directly to you in case you wanted to share it.
Oh,
but
right. Okay.
now
Yeah,
that
no, I
you
will.
let everyone know,
Yeah.
I'm happy to put it. I
I
just
want
know
to see
that's
it.
I just know that that's the first version and it has undergone revisions. So I didn't know
Yeah.
if you wanted to plug that one or just say that there's something coming soon.
I mean, let's plug this one and just say keep an eye on the website, and there'll be another one coming soon. It's a little bit on the rough side on this one, but just excuse it. It's fine. It's a long paper.
But it does have, you know, some of those nice figures that you showed and the kind of cheat sheet for how to potentially handle this when people are out in the field.
Sure, it does.
All right, any more questions?
If anyone's sort of interested in, you know, not just this kind of head-banging sedimentology part, but just the general, like, overarching Anthropocene part as well, and what humans are doing in the environment, we do cover all sorts, you know, Anthropocene sediment network, and we've got some pretty, I don't know, we've got a pretty diverse group of some really cool people, you know, from artists all the way to architects and engineers and stuff. Yes, thank you, Professor. I should have like pre-prepared these links. But yeah, so if you are interested in that, please do just drop me an email and we'll get you hooked in. We're not massively active at the moment, but that is going to change in the next couple of months when these papers come out. So yeah, just let me know. And also pass on to anyone who you think might be interested too. So yeah, just it's not all just headbanging sedimentology. We just need the rigor behind the science before we can start getting excited with the science.
All right. If there are no more questions, I'm going to thank Catherine for a fantastic talk. And then next month, on November 20th, we are going to hear from Arvid Singh on, let me check, because we had a text earlier today, connectivity in patterns and processes of river networks across scales. So we will be sharing registration links through the typical avenues over the following days. Thank you all for joining, and I hope you have a great day. Have a good one. Thanks.
Thank you.
Thank you.
Thank you, Catherine.
No problem.